We're going to look at, there are two parts to the fundamental theorem. In our book, I think they've got them kind of backwards in our book. Let me look at our book for a second. Nobody has the hard copy of our book, right? Oh, there's one right there, actually. They call this, they call this part 2 of the Fundamental Theorem of Calculus, which is a little strange. Normally, this would be called the first fundamental theorem, and the other one that they call part 1 would be called the second fundamental theorem. But so let's make a note of that. In our book, they call it the fundamental theorem part 2. Okay? And this is the one that has to do with our shortcut for adding up areas under curves. And we've talked about some reasons for doing that. For example, in physics, a lot of times the quantities in physics, important quantities, are defined in terms of integrals, even though in your physics class, your algebra-based physics class, you'd never see it that way. But like, for example, work, I think, is the one we used, right? Work is the area under a force displacement curve. What about something like impulse or change in momentum? That's the area under a force time graph. Okay, and so really, I mean, fundamentally, it's all calculus stuff. But if you're going to say accelerations are constant, which is not very reasonable in the real world, then you can do away with the calculus. And we'll talk today, remind me if I forget, we'll talk about why it is. When we get up to the geometric areas, we'll talk about why it is that we don't really need calculus for your physics class. Okay, but in reality we do. In college you will. Okay, so here's a quick reminder of what the first fundamental theorem says. Here's our trick. So if we have a definite integral defined like this, and what is that saying? What's that asking us to determine here in terms of area? The limits of integration would be from a to b. From x equals a to x equals b, we're looking at finding what? The area under what? Under that curve, right? Little f of x, okay? Good. So that's our area. By the first fundamental theorem, or part 2 if you want to call it that, it's equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. And here's our shortcut notation for that. Whoops. Okay, that's what that little bit at the end there says, where a is at the bottom and b is at the top. That's telling us to evaluate from a to b. So evaluated at b minus evaluated at a is that difference. So let's practice this one. So let's evaluate this integral right here. Okay, the integral of sine x plus cosine x dx. Okay, and let's just talk about just some minor techniques. And we haven't done a ton of anti-differentiation, but really most of this is just anti-differentiation until you get to the end where you plug in the limits of integration. Okay, so how would we go about this one? Okay, so what is the integral of sine x plus cosine x? It'd be cosine x, well, almost. What's the antiderivative of sine x? And you guys haven't had a chance to really memorize these yet. Negative cosine x plus sine x, right? Which we could just, why don't we make that sine x minus cosine x? We'll flip them around. Okay, so one thing we could do here also is we're able to split this up and integrate term by term, right? So we could rewrite this as the integral of sine x dx over our limits of integration plus the integral of cosine x. Something like that, right? And then that's going to give us negative cosine x evaluated from negative pi fourths to, 7 pi fourths. We could even do that. And I could put that negative out front if I want to, right? That's another cool thing I can do when I'm evaluating my antiderivatives. I can pull constants out in front of this, and just everything inside the brackets would just be, that would then just become cosine of the top limit minus cosine of the bottom limit. And I could find that value and then redistribute any constants out front if I want to. Does that make sense what I'm saying there? Okay. I can do it that way, or I could think of it as one big expression over the limits. Take your pick. Doesn't really matter. Sometimes it does. Sometimes there's a benefit to splitting it up. In this case, there wasn't really a benefit, but you'll see some examples here soon where there is. So if we do this, then what are we going to get? If this, let's kind of color code these here a little bit. Let's see, what do I want to do? I probably want to do, I'm just going to do this. Let's just, there's really no benefit for doing it this time. Let's just go like this. You saw we can do it that way. I guess it's good to make that point. But what I had written previously is just equivalent to this. Everybody get that? Okay, so we'll evaluate the whole thing at 7/4 pi. What's that going to give us? And let's color code this. So that's going to be blue, and this will be red. Whoops, this will be red. So evaluated at 7/4 pi, let's look on our unit circle. 7/4 pi is where? I guess that's right there. Okay, so we're going from there up to, or sorry, pi fourths up to 7/4. So we're going from there all the way around to there, right? That makes sense? Okay, so at 7/4 pi, what's going to be the value of cosine? Positive square root of 2 over 2, okay? But I've got a negative attached to that, so we're going to get negative square root of 2 over 2, and then the sine at 7/4 pi. Positive or negative? Negative, right? Because sine would be with a y coordinate. Okay, plus negative, so that's minus square root of 2 over 2. So there's our function evaluated at the upper limit, right? Minus our function evaluated at the lower limit. What's that going to look like? At pi fourths, cosine is positive, right? So I got to attach that negative sign. Plus at the sine of pi fourths is positive. Oh, why did I put pi fourths? Plus the sine of pi fourths would be positive square root of 2 over 2. So that whole thing just goes to 0, right? So what's my answer then? So I end up with we do that right? Antiderivative of sine is negative cosine. Yeah, that's right. Okay. Negative, yeah, that's right. So we end up for our total area then, our total area would just equal what? I guess negative square root of 2. Okay. Does that seem consistent with this picture? Because it needs to be. So there's the function sine x plus cosine x. Oh, it went from negative pi fourths. No wonder that was wrong. We were doing it from pi fourths. It's supposed to be from negative pi fourths. So negative pi fourths is right there, isn't it? Right? So at negative pi fourths, starting there, we would have had, this would have been a negative, and that would have been, this one would have been both negatives. Agreed? That makes sense? This should have been a negative pi fourths. And at negative pi fourths, that's actually down here. They're both at that place on the unit circle. We would have had the cosine would have been positive, but we're making it negative by multiplying by -1. The sine would have been negative. So this shouldn't have gone to 0. This should have been a negative. And I would have had negative the square root of 2 minus negative the square root of 2 equals 0. Everybody get that? Okay, so our total answer then looks like this. It looks like negative square root of 2 minus negative square root of 2 equals 0. Okay, does that look like 0 to you? How can that look like 0? Okay, negative area, right? What's our definition of negative area? I mean, how are we, which part is negative? Three-fourths pi to 7/4 pi. And it's negative because it's below the x-axis, right? And I think, did we mention that the other day? I think maybe we just briefly mentioned that. Okay, so so area is considered positive when we're evaluating it from left to right above the x-axis, right? And we did evaluate this from left to right, didn't we? We went from negative pi fourths to 7/4 pi. So we're moving from left to right, positive above the x-axis, negative below the x-axis. The total area of each lobe of that curve is equal, right? And so because this is negative, they just cancel each other out. Okay, make sense? Okay. Now, what would we have to do? We could construct a question that said, calculate the total area between the axis and the x-axis and the curve, where we're considering all area to be positive. That would be like the gross area instead of the net area. How would we have to do that? Any ideas? Yeah, we'd have to do, okay, but if we just do an absolute value of the whole function, we'd still get 0, right? If we went from negative pi fourths to 7/4 pi, if we add up that integral from negative pi fourths to 7/4 pi, I get 0, and the absolute value of 0 is 0. How could it's the right idea, we need an absolute value, but how am I going to carefully parse out all of the area without any of it canceling? What do you think? You got an idea?
Just take the interval from negative pi fourths to pi fourths, and then take the interval of the negative function for 3 pi fourths, 7 pi fourths.
Okay, so we would go from, you're saying split it up from there to there and from there to there, right? Is that what you're saying? Yeah. So all we'd have to do is take the absolute value of the area of the function between all of the zeros, right? The zeros are where this thing potentially could change sign. It doesn't have to change sign. It could be that it just touches the x-axis and rises back up. But if I always break the function up so the limits of integration are broken into the interior solutions. It's going between the interior solutions. Then if I take the absolute value of each of those subintervals, I'm guaranteed to come up with a positive area, right? Does that make, we'll look at one like that later. Okay, so some other stuff. Now, look at that first example there. What do you think the answer should be to that one? Look carefully. So we're looking at this guy right here. Zeros. How'd you get 0? That's right.
From AA, so it's taking like a chunk of 0 with taking like a rectangle of 0.
Does that make sense? Okay. If the bottom and top limits of integration are the same, then there's no width to our interval, so we have no area, right? Okay. Okay, now what about this bottom one? What I'm looking for here is, I want to know, how is this related to this integral? Negative's right. Does that make sense? Okay, how come? Well, because let's just make the assumption here for a second that b is less than a. Okay, it doesn't have to be, but if it is, then this integral would be going from left to right. Agreed? So our picture would look something like this then, if we drew a picture that went with this. So let's just say that this is b. Well, let's make this a. We'll do this makes more sense. We'll go a and b, so that a is the left, b is to the right. Those are our limits of integration. Okay. So if I've got some area under the curve, then if my curve looks like this, then I'm just looking at this area in here, aren't I? Okay. That's what this integral would represent. Right there. Agreed? Okay, if that's the case, then this integral over here would represent adding up the area backwards, right? Because the definite integration presumes that this is going to equal the antiderivative of f evaluated from the bottom limit to the top limit, from b to a. That's backwards, right? We're adding up the area in this direction, and that's negative area. Okay, we consider area to be positive when added from left to right and negative when added from right to left. Okay, and so yeah, you're right. These are off by, they're related. Whoops. They're related by, come on, where's that thing going? There we go. Right, that's how it's related. So they're opposites of each other. When you add area up in opposite directions of the same intervals, then they're opposites of each other. Okay, make sense? Okay. Give me 1 to 5. How are we doing? Good? Good? Okay. Okay, what about this one? So what's this saying? This is saying that if we were to add two integrals up, so the integral of f of x from a to c plus the integral of f of x from c to b, does it make sense that that's equal to the integral of f of x from a to b? Okay. The reason this works is because these two numbers match up, right? The upper limit of the first integral coincides with the lower limit of the second integral, right? So in other words, if I think of this as two areas, it just looks like that, doesn't it, right? This, whatever that is, orange or red area, is the area under the curve starting at A and ending at C. The green area is the area that starts at C and ends at B. Well, those areas add together to become the single area that starts at A and ends at B. Okay, so whenever you get these two spots matching up, we can combine that into a single area function. Okay, does that make sense? Give me thumbs. Does that make sense? Okay, you might be wondering what happens if C is not a number between A and B. Does it still work? Like what if we had, for example, something like this? Let's see, let's pick that color scheme. What if I had the integral of some function from 1 to 8 plus, supposed to be a dx there, plus the integral of the same function from 8 to 4. Is that equal to the integral of the function from 1 to 4? Okay, it is. It is. And here's why. Still works. Here's a picture of that, right? So the first integral would just look like, make that a little smaller. The first integral would stretch all the way from A up to C. That would all be positive, right? The second integral would go from C backwards to B. That would be some negative area that gets subtracted from the whole positive orange area. And what do you end up with? You end up with this little bit of positive area that's reckoned from A to B, right? So it still works. It always works as long as these numbers match up. As long as these two numbers, whoops. I didn't have this thing set up very well. As long as these two numbers are the same, it's always going to work. That theorem always holds. Okay? Okay, what about this one? Does this make sense? For even functions, think about the definition of an even and an odd function for a second. We've got these tests for even and odd functions. The even function test just says, is f of negative x equal to f of x? If it is, then it's even. The odd function test is f of negative x equal to negative f of x. If so, it's odd. Think about the symmetries they have, right? If we look at an even function, what's an example? Like x squared would be even, right? So an even function is a function with folding symmetry or reflective symmetry about the y-axis, right? So the question is, what's going to happen if we integrate an even function over symmetric limits of integration? So if we're going to go from negative a up to positive a. So we're going to get that piece and that piece. What can you tell me about the areas of those two pieces? They're the same, aren't they? Right? So therefore, I could make this a little bit simpler by saying, okay, instead of adding up the area of this even function from negative a to a, I could make the limits of integration a little bit simpler and just go from 0 to a and double the area, right? There's an advantage to that. Using 0 in our limits of integration is really nice because when we go to evaluate the antiderivatives, evaluating things at 0 is really simple, right? Oftentimes stuff just goes to 0. Okay, what about odd functions? You can already probably see what's going to happen here. With odd functions, they have symmetry, look at x cubed, about the origin, right? And so if we go from negative a up to positive a, well, what's happening there? They're going to add 0, aren't they? Because the total area of each part is going to be the same, but one's positive and one's negative. And so we end up with those results. Okay? Real handy. Okay, let's practice a little bit. So I'm giving you some areas here of two different functions, f of x and g of x. Okay, so we know integral of f of x from 2 to 4 is equal to 2. Integral of f of x from 2 to 7 is equal to 6. Integral of g of x from 2 to 7 is 2. Okay? So what's going to be, what about the first one there? What's that going to be? 0. Yeah. That's 0 because of the limits of integration, right? How about this guy? You sure? G of x? 4. There you go, right? And what's the reason? Because of that 2, right? Well, the reason is because this is equal to 2 times the integral of g of x dx from 2 to 7. I can pull that 2 out front, so it's 2 times the area, right? And so this is therefore equal to 2 times 2, which is 4. Okay? How about this guy? Yeah, negative 4. How come? Because I can break it up into the difference of those two separate areas, right? I could write this as the integral of g of x minus the integral of f of x, right, over those limits, which is just 2 minus 6. Negative 4. Okay. How about this guy? What's that going to be? Negative 2. Okay. We're just taking these limits of integration and reversing them, so it changes the sign of the area. How about this one? Yeah. 4 is correct, yeah. How'd you get 4? Okay, yeah, that's a good way to do it, I guess. Yeah, that's interesting. So you could say, yeah, that makes sense, right? So you could say if the total area from 2 to 7 is 6 and the area from 2 to 4 is 2, then it's true that you could subtract this lesser area from that total area. That's one way to do it. That's good. There's another way to do it. Anybody else come up with another way for that one? That's a good way to do it. Probably the easiest way to do it, actually. Anyone come up with a different way? Using the interior limit theorem? That was the one where we had, I'll show you. So what if we did this? What if we flipped this around? So we said this area is equal to the limit of f of x from 4 to 2 plus the area under f of x. Man, this thing doesn't write well. From 2 to 7. That works because the interior limits match up. Make sense? Okay. And what's that equal to? Well, f of x dx from 4 to 2 is just the reverse of this area, isn't it? So it'd be negative 2 plus, that was 6, right? Either way, doesn't matter. Either way, you're going to get 4. Okay, and then finally, that last one, that's no big deal, is it? That's just going to be 0. Yep. Okay. What do you think? Top one? Negative 32. Good. Everybody see why? We're just flipping this around. It's just this integral that's presented to us with reversed limits of integration. Okay, what about the second one? Yeah. Everybody see that? Okay, and here's a justification for that, because this is equal to 1/6 times the integral of 6x times 4 minus x dx from 0 to 2, right? 1/6 times 6 is 1. And this whole area is 32, so we just get 32 over 6, which is 16 over 3. Okay, good. Next one. Negative 64. Good, because I've got double this. What about that bottom one?
I mean, we could like plug in the numbers, but is there a way to find it from what we already have?
There's not, right? There's not enough, other than doing the integral, everybody see there's not enough information there? We're not given any information about the area under this function from 2 to 4, so we can't do anything. You can't just double it, right? Because the function might have completely different areas between, I'm sure it does, between 0 and 2 and 2 and 4, right? So not enough info on that one. Okay, so sometimes it's just much, much easier to evaluate definite integrals geometrically. Whenever you have areas defined by non-curves, where we just get linear functions, right? Just add them up geometrically. And this is why, by the way, algebra-based physics works, right? Because you're always assuming the areas are capped by these linear functions. And so it's easy to come up with geometric formulas for the physics formulas, right? So this is one where we would just break this thing up. I mean, here's what I would do on this one. I would just break it up into 3 pieces. Rather, I don't even make it a trapezoid, honestly. I would just make it rectangle, rectangle, triangle, and add them all up, right? No big deal. Does that make sense? And the trick there is just to think about this in terms of a geometric area, okay? How would you know to do that? Because these are lines, right? Anytime you get areas under lines, you can just add up area geometrically. Okay, I just want to make a point on this one. So let's just practice one of these really quick. So there's no trick to this. We just have to crank through this definite integral. So what do we get? What's the antiderivative of 3x? 3/2 x squared. Antiderivative of square root of x? 2/3 x to the 3/2. Good. Now we're evaluating that from 0 to 4. What's going to happen at 0? When I plug 0 in for x, I'm just getting 0, aren't I? So it's pretty nice. You can see the advantage of having a lower limit of 0 then, right? So this is really just going to equal 3 halves times 4, which is 6, plus 2/3 times 8, 4 to the 3 halves. See how I got 8 there? When you do a fractional exponent like that, you always do the root first. So that'd be the square root of 4 cubed. Gives me 8. So 16/3.
Wait, wouldn't the first term be 3 halves of 16?
Oh, you're right. 16. Yeah, 3 halves of 16. Yeah, you're right. Yeah, what was I doing? How did I get 4? I don't know. Right, so 16 times 3 halves, which is, what is that, 24? Is that right? Minus 0. Okay. So 72, what is that? 88/3 would be our answer. Okay, good? Make sense? Okay, what about this one? This one's kind of cool. So this is one where finally we get to one where it makes sense to split this up. How come it makes sense to split this up? Because our limits of integration are symmetric, right? Look at these two pieces. Sine is even or odd? It's odd, right? 2 is even because it's 2x to the 0, and 0 is an even number, right? So this is one where we'd want to do it like this. We'd want to break this thing up into separate parts. We'd want to integrate term by term, and look what we get. We get the integral of an odd function over symmetric limits. What's that equal to? 0. Yeah. So this one, you see the benefit here? This one just goes away. Minus, here I've got an even function integrated over symmetric limits, so I could make this easier. I could make this 2 times the integral of 2 dx from 0 to 7 halves pi, right? And what's that going to give me? What's the integral of 2 dx from 0 to 7 halves pi? Just 2x, right? Everybody get that? 2x times -2. So this is just equal to -4x evaluated from 0 to 7 halves pi, which is just -14 pi. So much, much easier if you use that little trick, right, in this case. And what gave it away? The red flag here to tell you to do that was these symmetric limits of integration. You always look for that stuff when you have symmetric limits. Okay.